Now that we're familiar with parametric equations, let's do some calculus on them. Finding the derivative of a parametric curve with respect to x using the chain rule, we see it is simply dy dt over dx dt, which should totally make sense since we know rate is change in y over change in x. Using the chain rule again, we can find the second derivative as well. So let's do an example. Remember, this is an example we did in the last packet. Here is the graph. So let's find dy dx. And remember that it is just change in y with respect to t over change in x with respect to t. So let's find dx dt and dy dt real quick. Now we divide and get dy dx. Now let's analyze this some more. Find critical values, then intervals of increasing and decreasing. So to find critical values, we set dy dx equal to 0. So our first critical value is t equals 0. And we end up with two more critical values, t equals 2 over the square root of 3 and t equals negative 2 over the square root of 3. At t equals 0, we have undefined slope. And the other critical values give a slope of 0. Now that we have the critical values, slope undefined or 0, we can look at the intervals of increasing and decreasing. Remember, a curve is decreasing when dy dx is less than 0. The graph is decreasing on negative 3 to negative 2 over square root of 3 or 0 to 2 over square root of 3. Let's look at the graph to make sure this matches up. So from -3 to -2 over square root of 3, it's definitely decreasing. Even though we are going in the opposite direction that we usually do with x and y, it's still decreasing. And from 0 to 2 over square root of 3, we can also see the graph is decreasing. Now we look at where the graph is increasing, where dy dx is greater than 0. And those intervals are from -2 over square root of 3 to 0, or 2 over square root of 3 to 3. Looking at the graph, we can see that the graph is definitely increasing on those intervals. Now let's look at concavity, which has to do with the second derivative. We do this by taking the derivative of dy dx with respect to t, then we divide by dx dt. Now we divide this by dx dt. Simplify a bit. And so our second derivative with respect to x is 3 over 4t plus 1 over t cubed. Now we find the critical values, which are possible inflection points, by solving the second derivative equal to 0. T equals 0 is still undefined. And so now we know that the graph is concave up, second derivative being greater than 0 on 0 to 3. And we know the graph is concave down, second derivative less than 0, from negative 3 to 0. Now we look at areas under the curve for parametric equations. We will start by looking at an example of a cycloid, where x of t is t minus sine of t, and y of t is 1 minus cosine of t. We take an interval from a to b and splitting it up into a bunch of rectangles. Note, since everything is in terms of t, that the height of a typical rectangle is y of x of t sub I bar, and typical width will be x of t sub I minus x sub t sub I minus 1. The length times width in terms of t, as we see here, and setting up the Riemann sum, doing a little manipulation of multiplying the sum by 1 to get delta t and sum. And notice, now we have a rate of change in terms of x. Then taking the limit to get the exact value, we get this nice integral. And here's a theorem that states what we just did. Now an example. Starting this problem, it's enclosed by the y-axis, where x equals 0, so we can find the bounds for t. So we're going from t equals 0 to t equals 2. And we have this area formula we can use. We just need x prime of t. And now we can evaluate. And now we know the area under the curve from t equals 0 to t equals 2. Not a bad idea to get in terms of y and look at the graph. Then figure the area out to make sure it checks out. And here is the curve in terms of x and y. And here's the graph on Desmos. Remember, t equals 0 to t equals 2 is where we are going to, which corresponds to the graph at 0, 0, and 0 square root of 2. Now let's look at bounds real quick. Remember, x equals 0. And we know we only want the positive square root of 2 since we're going from t equals 0 to t equals 2, as we see on the graph.